Video, we explore whether real regular expressions are regular or not. If they are not regular, what are they? We discuss real regular expressions and context free languages, context sensitive languages, Turing machines, and more. Before we dive into regular expressions, we discuss what regular languages are. A specified alphabet or set of symbols is used to form a set of strings known as language. Within the set of all strings, regular languages constitute a subset. So, what are regular languages? Regular languages can be defined as languages recognized by finite automatas such as NFAs and DFAs. Theoretical regular expressions are equivalent in power to NFAs and DFAs, which means theoretical regexes recognize regular languages. This is a depiction of the traditional Chomsky hierarchy. As we see, regular languages and finite state automaton are at the bottom, followed by context-free languages and PDAs which are equivalent in power. Then comes context-sensitive languages and then Turing machines. We know by the Church-Turing thesis that Turing machines are equivalent in power to the human mind. In this video, we'll explore where do regular languages fall, that is, what are the bounds of real regular expressions. Let's now discuss the history of real regexes. In 1943, Warren S. McCullough and Walter Pitts began to develop models that described how the human nervous system works. Their research focused on trying to understand how the brain could produce complex patterns using simple cells that are bound together. In 1956, mathematician Stephen Kleene described neural models with an algebra notation that he penned regular expressions. After this, influenced by Kleene's notion, in 1968, Ken Thompson, a mathematician and Unix pioneer, implemented the idea of regular expressions inside the text editor ed. The regex in the fourth bullet on the slide is an example of how one of the first regexes in used to look like. This regex read the word pinky. In 1970, Alfred Ahos extended it with a whole bunch of new functionalities, modified syntax. His program was able to translate any regular expression to a finite, deterministic finite automaton. Post that, in 1987, Larry Wall introduced Perl programming language, which uses C-regex library, but over time, it became many more powerful functionalities were added to it. Finally, today, despite being hard to read, hard to validate, hard to document, and notoriously hard to master, regexes are still widely used today. Supported by all modern programming languages, text processing programs, and advanced text editors, regexes are now used in more than a third of both Python and JavaScript projects. So now, what are some characteristics and features of the real regular expressions that we use today? Characters and escape characters. Characters are part of the string and escape characters are language-specific things. Or and operators are similar to what we have in theory, or which is represented by a pipe, and which is used to append strings together. The character class. In regexes, we have the bracket operator, where we can have a class of characters repeat multiple times. The plus, the clean star operator, the question mark, and the mn are things that regular languages have. These were all the things that regular languages had. Beyond these, we have things like the \1, \2, etc., which are back references, which makes real regular expressions that are used today much stronger than the theoretical ones, since it is like maintaining a memory of sorts. Similarly, we have the look aheads and look behinds, which simulate a stack of sorts that can go ahead and back to check in the string itself. And then we finally have the if then else statements that give real regular expressions more of a programming power of sorts.
So let's now try to characterize the power of the real regular expressions. So what we can do is we can show an equivalence between the formal regular languages and the real regular expressions. So recall that a regular language, R, is one of six things. So we can either have the empty set, the the regex that matches nothing, the empty string, either or like a single symbol. And we have these three primitives, but then on top of that we have the concatenation operation, we have the alternation operation, and then we have the clean start. Now all six of these can be supported by the real regexes. For the empty set, you have the question mark, exclamation mark, and so this regex matches nothing, and so therefore you have the empty set. You can have the empty string. You have a start symbol, but then you don't specify what to match next, and you have the end delimiter, and so you end up matching just the empty string. And then finally you can match a single symbol, and you can combine these using like this simple concatenation or the pipe and the star. And so you can show that, okay, a real regex can sort of define every regular language that way. But that's only the surface. Real regexes can do much, much more. And one thing they can do is match palindromes. And we know palindromes to be non-regular. So if you look at the following regex, let's break it down. So the question mark 1 is sort of the key element here, and what that does is that it recursively applies the regex rule, and this is supported in languages like Perl and Ruby. And that already breaks away from our sort of formal understanding of the regular languages, this idea of recursion, right? But then we also have this idea of a back reference and capture groups. So if you look at the regex, the dot within the parentheses is matching any character, and then the question mark 1 is recursively applying this regex on top of that, and so you keep reading in characters and matching them. But in the back reference, the \2 is back referencing the second capture group, and so that allows it to detect, okay, the last character needs to be the same as the first, the second last needs to be the same as the second, and so on and so forth. Now that's the left-hand side of the alternation, and the right-hand side is optionally matching a single character. And the whole purpose of that is to now be able to read in odd versus even length palindromes, in which case the dot would be matched for an odd length palindrome. And you can plug this into a Perl sort of regex checker, and you can see that it does, in fact, recognize palindromes and rejects non-palindromes. And so, coming back to our characterization, we can immediately conclude that palindromes, because we can match palindromes, we can match something beyond the regular languages. So we started with regular languages, and we now know that, okay, these real regexes can match something beyond the regular languages. Now let's look at the context-free languages. So the context-free languages are pretty simple in terms of their definition. We have the four-tuple definition. We have a collection of non-terminals and terminals. We have some productions which tell us, okay, given a non-terminal, how to use that and replace that with a sequence of terminals and non-terminals. And then we are given a start symbol, so where to start with. So we know some very straightforward context-free languages. The palindrome is one such context-free language, which we know we can match. But we can immediately show, by example, that these real regexes can match something more powerful than the context-free languages. And we show that we can give a real regex for the language WW, where W belongs to sigma star. And so the way you can do that is you can quite elegantly express this language using capture groups and a back reference. So again, the dot star matches any arbitrary string. The parentheses enclose it, marking it as a capture group. And finally, the back reference says, okay, match the first capture group again. So given that you've matched W, match W again. So you match WW. Now coming back to sort of our characterization of the power of the real regexes, we know that WW is not context-free. And this tells us that the expressive power of the real regexes is more expressive than the context-free languages. So we know that our real regexes are more powerful than the context-free languages. Now, this begs the question, okay, are they context-sensitive? So recall that a context-sensitive language has productions of the form, if you have XAZ, so A is your non-terminal, then it gives XYZ. Now this is contingent on A being preceded by X and being succeeded by Z. Another fact is computationally a context-sensitive language is equivalent to a linear bounded Turing machine. So basically the tape is now limited to the input string and then the start and end markers beyond that, surrounding that input string. And so now coming back to the context-sensitive languages, we can attempt to craft a regex for the rule above. And the way you can do that is you can simply have a look behind assertion and a look ahead assertion. And so now you only produce XYZ if you have X, if you have A preceded by X and Z succeeding A. So now that we've shown that our real regexes can express something more powerful than the context-free languages, it naturally brings the question, okay, are these real regexes context sensitive? So recall that a context sensitive language has productions of the form XAZ gives XYZ, and so A will only produce Y if it's preceded by X and it's followed by Z. So what we can do is we can attempt to craft a regex for the rule above, and that does exactly that. It produces Y from A as long as it's preceded by X and followed by Z. Now the key limitation here is that this look behind that we've used, look behind to check if it's preceded by X, is fixed width. To sort of really have true context sensitivity, we would need variable width look behind. And so we can conclude that while we can match some context sensitive languages, whether we can match all of them appears to be unclear at this point. But we have tried to sort of formulate a rule. Okay, given a context sensitive rule, how can we directly map that to a real regex?
So, after all this discussion, we already now know that real regexes are context sensitive, and we can prove that by thinking about how being context sensitive would mean that we can simulate linear bounded Turing machines in them, and that can be done using if and else statements, where we can have an if then and else statement to talk about to refer to a previous cell in the real regex or a previous value that the real regex might have recognized, and then we can confirm if that value or that string appears again in the string at a later point. Moreover, we can check for things that have previously occurred in the string using parentheses and lookbacks and lookaheads in real regexes, so that we can make strings like context sensitive strings using real regexes. Moreover, this shows that real regexes are not only context free but also context sensitive, and context sensitive grammars can be modeled using real regexes. Now, moving on to the limitations of real regexes and whether or not they're Turing complete. Turing completeness being the final frontier that we humans can think of, right? So, real regexes can be thought of as the regex strings in programming languages, those strings that we write in programming languages like Python, JavaScript, or any other language. And we can think of them as also being equivalent to the regexes that we write in a theoretical class. But real regexes are much more. When we consider a real regex, we should not only consider the string that we can write in a regex, but the complete regex package in many programming languages. And in that package, we can do a lot more than just recognize strings. So the limitation that we face till now that stops regexes from being Turing complete is that they can only recognize strings and they cannot create or generate new strings. But that is where real regexes come in. So if we think of the whole regex package, then we can also do matches, replacements, substitutions, and we can also generate strings by using the find and replace method that is included within the multiple regex packages. So by using the find and replace functionality that multiple regex packages have, and also using the substitution functionality, which looks back and checks for parts of the string, we can actually generate new string from, let's say, a string that does not exist, or based on an existing string, we can generate a new string. Therefore, by being if a regex in this scenario is given an input string like the input tape of a Turing machine, then after running a match and replace action on real regexes, we can create a new string and we can therefore create new values and the output part of a tape using said real regexes. But this, even though this brings real regexes closer to the functionality of Turing machines, as now they're not only able to recognize but are also able to generate content and able to compute on content. This is not a definitive proof of them being equivalent in power to Turing machines. So, how do we go about proving that? Well, let's move on to the next slide, where we see that they are actually Turing complete. And this can be found using a very clever function in modern real regexes. So, as we've been talking about, the regex strings that we can write have multiple functionalities, which include the clean star, the odds and the and signs, and the look backs, look aheads, replacements, parentheses, and all of those other things that we have till now used to prove that they're context free, they're context sensitive, they can make regular languages, and everything else, right? But there is one other functionality in real regexes, which is there, which is that we can actually embed Perl code in regexes when written in Perl. So the regex package in Perl actually allows you to embed Perl code right there in the regex, which on execution would go on to execute the Perl code like any other piece of code. And as we know that Perl is a Turing complete language, therefore it can perform all the operations that any other Turing machine, from a simple calculator to a supercomputer, might be able to perform given enough time. Therefore, by embedding Perl code in regexes, we are able to execute and run any code. And thus, we can show that this helps us complete our proof. And as Perl is a Turing complete language, and we can write Perl code in regex, and we are able to perform all these computations, we therefore prove that real regexes are not only regular, but on top of that, they're Turing complete. And thus, they're as strong as any other Turing complete system. Now, after all this discussion, we have proven that regexes are not only regular, but they can also be used to create context free grammar and context sensitive grammar. And now we have also proven that with the power of Perl code being written within regexes, they're Turing complete. But is this the final constraint? Well, sadly, this is the final bound. As by the Church Turing thesis, we know that anything that we humans can understand and thus program is upper bounded by Turing completeness, as the human mind itself is Turing complete, and we cannot generate anything greater than that. Therefore, real regexes, which are Turing complete by the virtue of them being able to use Perl code, are upper bounded by being Turing complete, and it is not possible for them to be anything more than that. So that completes our exploration of whether real real regular expressions being regular or not. And we conclude that by saying that they're not regular, but are instead Turing complete. Thank you.